Hello everyone, today's spotlight and review is going to be on hybridization. Okay, like I mentioned, you should have discussed hybridization in OChem 1, but I think some of this may be a review for you, and then some of it may be an expansion on what you've thought of previously regarding hybridization. So the first thing I wanted to do is talk about hybridization of carbon. And let's look at an sp3 hybridized carbon. So for example, in methane, right, we have a carbon that's a central atom, and it's going to undergo hybridization of its atomic orbitals. So this picture over here that I'm circling with the mouse is carbon's electrons in its atomic orbitals. So you guys know that it has 2 electrons in its 1s orbital, 2 electrons in its 2s orbital, and 2 electrons in 2 different 2p orbitals. So these are the atomic orbitals and the electron configuration in those atomic orbitals. So in order to do VSEPR, right, to have the groups, the maximal angle apart that they can be from each other, the orbitals undergo hybridization before bonding. So I just wanted to point out that the 1s electrons, these are our core electrons. These don't change or hybridize. And so we are, from this point on, just going to be ignoring the 1s electrons for carbon. And after this slide, we'll be focusing just on the 2s and the 2p, which are the valence electrons. Everybody knows that carbon has 4 valence electrons. Those are the ones that are going to, these orbitals in particular will hybridize, and these electrons, the valence electrons, will fall into the hybridized orbitals. So when carbon needs to make 4 sigma bonds with 4 different atoms, for example, these 4 hydrogen atoms, then it will hybridize its 2s orbital and all 3 of its 2p orbitals. Right? So all 4 of these orbitals hybridize to form now 4 sp3 hybridized orbitals. And we call it sp3 because it's 1 part s and 3 parts p, right, from the atomic orbitals that combine to form the hybridized orbitals. And because there's 4 valence electrons, the electrons will fall into the equal energy or degenerate orbitals one at a time, and will not pair up unless we have a 5th electron, which we do not have. So that means that there's 4 sp3 hybridized orbitals, each contains 1 valence electron, and each of those will combine with hydrogen's 1s orbital to form a sigma bond with that hydrogen atom, forming methane. So let's talk about an sp2 hybridized carbon. For example, the carbons that you will find in ethylene, also known as ethene. So these carbons are forming 3 sigma bonds, right? 2 to hydrogen and 1 sigma bond to the other carbon, and also a pi bond to the other carbon. Because it's forming 3 sigma bonds, or it's attached to 3 different atoms with 0 lone pairs, we say it has a steric number of 3, and therefore it's going to do sp2 hybridization. So again, I ignore the 1s core electrons. I'm only drawing in the 2s and 2p orbitals. And I filled it with 4 electrons because carbon has 4 valence electrons in its electron configuration. After hybridization, right, we are hybridizing the 2s and 2 of the 2p orbitals to form 3 equal energy degenerate sp2 hybridized orbitals. That means that 1 of the 2p orbitals remains unhybridized. So I just took it and it moves right over here, right, and it looks exactly the same as it was, a 2p orbital remaining that is unhybridized. So the electrons will fall into these 1 in each orbital. This allows carbon to be able to make 3 sigma bonds. Again, 2 of those are with hydrogen, 1 is with the other carbon atom. using the sp2 hybridized orbitals. And then it has one remaining 2p orbital, which we often just call a p orbital, and one electron in there to do the side-by-side overlap to form the pi bond with the other carbon. So this is the electron configuration in the orbitals after hybridization. What about an sp hybridized carbon, such as that exists in acetylene, also known as ethine? So these carbons are only making 2 sigma bonds, one to a hydrogen atom and one to the other carbon atom. And each carbon has 2 pi bonds as well. But because it's only making 2 sigma bonds, or it only has 2 atoms attached with 0 lone pairs, we say it has a steric number of 2, which means it only needs to do sp hybridization. So again, this is carbon's electron configuration. After hybridization of one of the 2s orbital and one of the 2p orbitals, we get 2 sp hybridized orbitals and 2 remaining unhybridized 2p orbitals. One electron will go into each orbital. The sp hybridized orbitals will be used to form the sigma bonds, one to a hydrogen and one to a carbon. And then the 2p orbitals will be used to form 2 pi bonds with the other carbon that are what we say orthogonal or 90 degrees apart from one another. Okay, let's talk about the carbocation, right? So for example, I have this carbocation over here. You can see that carbon has a formal positive charge and is electron deficient. How does that change the electron configuration? Well, what we have to do is subtract an electron because of the positive charge on the carbon. So it actually only has 3 electrons in its valence shell. And because it's making 3 sigma bonds, each in this case all to hydrogen, so 3 sigma bonds, it needs to hybridize to sp2, which means it'll hybridize its 2s and 2 of its 2p orbitals to form the 3 new sp2 hybridized orbitals. That will leave one of the 2p orbitals remaining unhybridized. There's only 3 electrons because we subtracted one, so we're only able to put 1 electron in each of the sp2 hybridized orbitals. Each of those will be used to combine with an electron from hydrogen's 1s orbital to form the 3 sigma bonds with hydrogen. That leaves the 2p orbital empty. So it's important to recognize that the carbon of a carbocation is sp2 hybridized, and it contains an empty p orbital. So there is a p orbital at that carbon. This is going to be very important as we start to talk about aromaticity, right? We need to understand that at this carbon there is a p orbital. It does not have any electrons in it, right? So it is an electron deficient p orbital, creating the fact that this carbon is an electrophile because of its electron deficiency. What about a carb anion, right? And specifically a carb anion with a localized lone pair. So let's look at this simple carb anion. The carbon now has an extra electron and is negatively charged. Because there's an extra electron, we add an additional electron to carbon's valence shell. That's why it has a total of 5 valence electrons here. Because carbon is forming 3 sigma bonds, each to hydrogen atoms, we need to hybridize. Oh, I'm sorry. And it has a lone pair, so we have to count that to the steric number. Right? So 3 sigma bonds and 1 lone pair is a total of a steric number of 4. If it has a steric number of 4, we're going to hybridize all of the 2p orbitals along with the 2s orbital in order to get 4 sp3 hybridized orbitals. Since there's 5 electrons, we will put those 5 electrons into the hybridized orbitals, and the 5th electron will form a pair, right, with one of the other electrons. So we do have a lone pair, and that lone pair exists in an sp3 hybridized orbital. So that's important to recognize, is that there's a lone pair of electrons, right, which matches the structure over here. we understand what orbital it's in. It's in an sp3 hybridized orbital. And because it's in a hybridized orbital, it's what we call localized. Okay, so when the lone pair exists in a hybridized orbital, in this case sp3, but in other cases it could be sp2 or sp, right? But if it exists in any kind of hybridized orbital, we say it's a localized lone pair, right? That's really, really important to understand, is that that carbon has a lone pair. It's in a hybridized orbital, in this case sp3, and because it's in a hybridized orbital, it's localized, meaning it does not delocalize over a series of atoms. Instead, it's localized on this carbon. The other 3 unpaired electrons will go on to form sigma bonds with a 1s electron from the 3 hydrogen atoms. Okay, is it possible for there to be a carb anion with a delocalized lone pair? And the answer is yes. Okay, and the hybridized orbitals involved are different than with a localized lone pair. So if we look at this carb anion, we notice that the anion is directly next to 2 carbons that have a pi bond between them. So let's see how this plays out into what's the preferred orbital for this lone pair. So again, we're starting with carbon's atomic orbitals, 2s and 2p. Because the carbon is an anion, we've added that 5th electron. After hybridization, right, notice that we are only hybridized to sp2 and not sp3 like the last example. Let's look at why that is. Normally, if you think about carbon, right, and you think, okay, it's making 3 sigma bonds and it has 1 lone pair, that should be a steric number of 4, and we should hybridize to sp3. But that's not the case when that lone pair is adjacent to a p orbital. When there's a p orbital right next door, then this lone pair would prefer to be in a p orbital as well, so that it can delocalize over a series of p orbitals. Let's look at the picture down here. This is 3 p orbitals right next to one another. If we place this lone pair, these 2 electrons, into one of these p orbitals, right, if it will be super stable if it can overlap with neighboring p orbitals. The reason why that makes it stable is because the electrons in that lone pair can delocalize over the entire series of overlapping p orbitals. Instead of having to stay localized at 1 carbon, now they're delocalized over a series of overlapping p orbitals. So when we have a lone pair that's allylic, right, it's delocalized and it doesn't count towards the steric number. So instead, what we're going to do is hybridize to sp2 because of the 3 sigma bonds from carbon, ignoring the lone pair. We don't count the lone pair, right, if it's a delocalized or allylic lone pair. So that means we're hybridizing 2 of the 2p orbitals and the 2s orbital to form 3 sp2 hybridized orbitals. That leaves 1 remaining 2p orbital unhybridized. The 5 electrons will fill in the way that you see here, with one of the electrons, the extra electron, moving up into the 2p orbital. So this is now the lone pair. Notice what orbital it's in. It's in a 2p orbital. It's not in a hybridized orbital. That's super important, right? If it was in a hybridized orbital, we would have said it was localized. But when you have a lone pair in a p orbital, or more specifically a 2p orbital, it's delocalized because it's not stuck in this 2p orbital, right? It's delocalized over a series of overlapping p orbitals. So it might look like it's higher energy up here in this 2p orbital, right? This 2p orbital is higher energy than these sp2 hybridized orbitals. It looks like, why would you have the electron higher energy, right, than it possibly could be if it was down here? And the answer is, it might appear that it's higher energy, but it's not, because it's not stuck in this orbital, right? It's delocalized over a series of overlapping p orbitals. So it's not localized in this 2p orbital, but instead delocalized, and that makes it more stable. So we can have a lone pair on carbon right? It can go into a p orbital or it can go into a hybridized orbital. If it goes into a hybridized orbital, it's localized on that carbon. That's not as stable as being delocalized. In order to be delocalized, it needs to be in a 2p orbital, right? It needs to be in a p orbital that overlaps with neighboring p orbitals. Let's talk about nitrogen for a little bit. I have drawn the structure of histamine here because it has 3 different nitrogen atoms, and they all behave a little bit differently, right? They're all different in what happens with hybridization and where the lone pair is. So it's good to highlight all 3 of these different nitrogen atoms and what is different about them. Let's start with this one over here on the very right. We're looking at this nitrogen, right? What does it have? It's making 3 sigma bonds, 2 to hydrogen atoms, 1 to this carbon, and it has 1 lone pair, and it is a localized lone pair because there are no p orbitals next door, right? So it's a localized lone pair, so we know that lone pair should be in a hybridized orbital. So let's look at nitrogen's electron configuration. Nitrogen's electron configuration is that it has 5 valence electrons, right? So I've filled out 5 valence electrons here. Again, it's going to go to sp3 hybridization because it's making 3 sigma bonds, and we also include the lone pair because it's localized. So it has a steric number of 4, so we're going to hybridize to sp3. As I fill in my 5 electrons after I've hybridized to sp3, I end up with 1 lone pair. Again, that lone pair is in a hybridized orbital, so I know it's localized on that nitrogen. It is stuck in this orbital, right? It is not spread out over multiple atoms. Each of the other unpaired electrons forms a sigma bond, either with hydrogen or with carbon, right? And I didn't write that here, but it says with hydrogen or carbon, forming the 3 sigma bonds for that nitrogen atom. Okay, let's look at this nitrogen in histamine. Right? It looks a little bit different than the one that we previously looked at. How many sigma bonds does it have? Right? It has 1, 2. So this one only has 2 sigma bonds, right? And 1 lone pair. This lone pair is actually localized. So we would expect it in a hybridized orbital. So because it's localized, it counts towards the steric number. So 1 for the lone pair, 2 for the 2 sigma bonds. So we're expecting sp2 hybridization because of the steric number of 3. To get sp2 hybridization, we hybridize the 2s and 2 of the 2p orbitals, which leaves 1 2p orbital remaining unhybridized. And that's this one here. And I'm sorry, I didn't write 2p next to it, but right here it should say 2p. This is just the 1 remaining 2p orbital that is not hybridized when you go to sp2 hybridization. So 5 electrons total. This is how the 5 electrons will fill the remaining orbitals. So the sp2 hybridized orbitals and the 2p unhybridized orbital. Notice that the lone pair is actually in a hybridized orbital and it is localized, right? There's 2 unpaired electrons. Those will overlap with the 2 carbons that are neighboring that nitrogen, forming sigma bonds. And then there'll be 1 unpaired electron in the unhybridized 2p orbital to form the pi bond with carbon. So this is a case where we have sp2 hybridization for a nitrogen, right? We do have a lone pair. It is localized, so it goes right into an hybridized sp2 hybridized atomic orbital. And there's also a pi bond associated with that nitrogen. You can see that second bond here between this nitrogen and carbon. That is taken into account by the 1 electron in a remaining unhybridized 2p orbital. Okay, the third nitrogen on histamine, right, again looks a little bit different from the previous ones. This nitrogen, if we count up how many sigma bonds it's forming, it's sigma bonded to this hydrogen and 2 carbons next to it. So it's forming 3 sigma bonds. And the question is, what about this lone pair? So this lone pair is actually allylic and delocalized. which means this lone pair should go into a p orbital, a 2p orbital, not a hybridized orbital. So it doesn't count towards the steric number. This nitrogen only has a steric number of 3. As a result, we are going to hybridize to sp2, right? So we're forming 3 sp2 hybridized orbitals and a remaining unhybridized 2p orbital. The lone pair, notice the lone pair is up in that 2p orbital because it can neighboring other p orbitals and it's delocalized. Okay. And we're going to find out that this lone pair is important for aromaticity because it's part of the overlapping 2p orbitals in the ring. This lone pair is not because it's localized. So localized lone pairs don't count towards aromaticity. Same thing with this one. It's localized. It does not count, right? And with aromaticity, we're specifically talking about rings, so we wouldn't care about this one anyway, right? But this lone pair does count, and it counts because it's part of the series of overlapping p orbitals in the ring. And we can see that it exists in a 2p orbital, delocalized with the 2p orbitals at all of the atoms in the ring. And again, as we study aromaticity in this chapter, I think that will make a little bit more sense to you. So it's forming 3 sigma bonds, right, with each unpaired electron in an sp2 hybridized orbital. And as one lone pair, it might seem like it's unstable in a 2p orbital, but again, it's delocalized over a series of, in this case, 5 overlapping p orbitals that all exist in a ring. Okay, so that's super important. The last one that we're going to look at is an sp hybridized nitrogen, right? Just like carbon can be sp, nitrogen can also be sp. Let's look at this nitrogen. How many sigma bonds is it forming? Just 1, right, with this carbon. And it has 1 localized lone pair. I know it's localized because it's not allylic. So that means it has a steric number of 2 because of 1 sigma bond, 1 localized lone pair. So if it has a steric number of 2, I should hybridize to sp. So I hybridize my 2s and one of my 2p orbitals. That means that I have 2 unhybridized 2p orbitals remaining over here. And I had a total of 5 electrons, so I should have a total of 5 electrons over here, right? Remember, we talked about this lone pair is not allylic, so it's localized. So it belongs in a hybridized orbital, in this case an sp hybridized orbital. This other electron in the other sp hybridized orbital is forming the 1 sigma bond that that nitrogen has with the carbon. In addition, there's 2 pi bonds being formed from this nitrogen to this carbon. So those are being formed from 1 electron in 2 2p orbitals, in this case, forming 2 pi bonds with the neighboring carbon. Okay, that's your review and on hybridization, and hopefully it helps explain some of what we're going to be talking about when we start talking about where lone pairs are. Are they in a hybridized orbital and they're localized? Are they in an unhybridized orbital? And so a 2p orbital and delocalized. That's going to be super important information for you to understand aromaticity. Thanks for watching.